In question 4a, we're asked for the charge carriers responsible for current in a metal. Well, this is electrons. The charge carriers in an electrolyte are ions. In B part 1, we're told a copper rod of cross-sectional area 3.0 times 10 to the minus 4 square meters is transmitting large currents with 650 coulombs passing in 5 seconds. Whereafter the current in the rod, well, current is charge over time, which is 650 coulombs over 5 seconds, which is 130 amps. In part 2, we're after the total number of electrons passing any point in the rod per second. Well, current is equal to the number of charge carriers times the charge on a charge carrier. So the number of electrons is equal to the current over the charge on the electron, which is 130 amps over 1.60 times 10 to the minus 19 coulombs, and this comes out at 8.13 times 10 to the 20 electrons passing in a second. In part 3, we're asked for the drift velocity of the electrons, given the number density is 1.0 times 10 to the 29 per cubic meter. Well, for this we can use the current is the charge carrier density, number of electrons per cubic meter, times the area times the drift velocity times the charge on the electron. So the drift velocity is I over N A E, and this is 130 over 1.0 times 10 to the 29 times the area of 3.0 times 10 to the minus 4 times the charge on the electron of 1.60 times 10 to the minus 19. This gives a drift velocity of 2.7 times 10 to the minus 5 meters per second. In C part 1, we have a copper rod of changing dimensions, and we're asked why the current in Y, the narrower part, must be the same as that in X. Well, by Kirchhoff's first law, the current in must equal the current out. In part 2, we're told rod Y has half the cross-sectional area of X. We're asked to calculate the mean drift velocity of electrons in Y. Well, we found before that the drift velocity is I over N A E. So if A halves, V will double. All the other properties are staying the same. This gives V2 as equal to 5.4 times 10 to the minus 5 meters per second.